Hello everyone, welcome to part 6 of my series on Diophantus. If you've watched the previous videos, you've seen several of Diophantus' big ideas for solving problems, but a lot of problems are still too complex for these to work easily. At the end of the last video, we saw an example where the basic principles point to a method that nearly works, but we had to play around with some constants before it actually gave us an acceptable solution. In this video, we'll look at how Diophantus didn't actually just use trial and error in such cases, especially after the beginning of his work. He preferred to analyse how to fix his method and to set that up as a subproblem. To see this in action, we're going to look at these 4 problems, and as usual I'd advise you to pause the video here and have a think about them yourself for a bit. So our first problem is to find a rational number such that both its cube plus 4 times its square and its cube minus 5 times its square are squares of rational numbers. Well, if we call the unknown side length s, effectively we need s cubed plus 4s squared and s cubed minus 5s squared to be 2 squares. Well, to achieve helpful form here, we'd like to set the sides of these squares to be some given multiples of s. The question is, what multiples should we choose? Rather than trial and error, think about scaling both squares down by a factor of s, so their areas by a factor of s squared. The sides become the 2 constants that we're seeking, and their areas become s plus 4 and s minus 5. In other words, 2 numbers that are 9 apart. So we've therefore got the following subproblem. Find 2 positive rationals whose squares are 9 apart. Now, Diophantus would now give his symbol s a new meaning just for the duration of the subproblem, but to avoid confusion I'm going to use a different symbol, t. We can achieve helpful form here simply by setting the smaller unknown to t and the larger one to t plus 1. We then have t squared plus 9 is the same as t squared plus 2t plus 1. The t squared terms cancel and we get t equals 4, and maybe you could just spot immediately that 16 and 25 are a solution to this little subproblem. Well, now we can go back to our original problem, and we know that the good thing to do is to set s cubed minus 5s squared to 16s squared, from which we can just read off the solution s equals 21. Well, here's the next problem, which forms a kind of pair with that last one. We're going to start similarly. We assign s to the side of the cube, so we've got some terms in s to the power 9. And to get towards helpful form, we then set the side of the square to a multiple not of s but of s squared, say 2s squared. Then we end up with 16 times s to the power 8 plus 5s to the 9 and 16 times s to the power 8 minus 3s to the 9. Both have to be squares. And again, with helpful form in mind, we just like to set the sides of those squares to some given multiples of s to the power 4. So we scale everything down, and so that the multipliers we're looking for just have to have the property that their squares are 16 plus 5s and 16 minus 3s. It's quite similar to the first problem, but because the differences between the expressions here have an odd rather than an even power of s, we've got a slightly different subproblem. Find 2 squares of which the larger is 5/3 as far above 16 as the smaller is below it. If we set the side of the smaller square, the one below 16, so the side is 4 minus t, then this will produce 16 plus 5/3 of 8t minus t squared being a square, and we can simply equate that with the square of 4 plus t, and then the t to the 0 terms, the 16s, will cancel and we'll get helpful form. Specifically, we get t squared plus 8t is 5/3 of 8t minus t squared. That rearranges to 8t squared is 16t, and so t equals 2. We can then check by plugging in the value, and we can find that 4 minus 2 squared, so 4 squared, 16, and 4 plus 2 squared, 36, are in the right proportions. So we go back to our original problem, and we know that the thing to do is to set 16s to the 8 minus 3s to the 9 is 2s to the 4 squared. So in other words, we have 3 times s to the 9 is 12 times s to the 8, and so we can read off s equals 4. And again, just always check that the solution really is an acceptable one with distinct and positive rational numbers. In fact, this pair of subproblems that we've seen so far actually go to solve quite a lot of Diophantus problems, especially in books 5 to 6. Right, here's our next challenge. It involves 3 unknowns and their squares, but also 3 further squares. So as explained in the last video, we start by making some substitutions to ensure that that latter kind of squares are definitely going to end up as squares. In particular, Diophantus sets the sum of the unknowns to be 5s squared, and 2 of them to be s and 2s, because this sorts out 2 of the conditions straight away. And that tells us that 5s squared minus 3s is the other unknown. So what we need to do is to ensure that 5s squared, the sum, minus the square of 5s squared minus 3s is itself a square. But this is an expression in S where the outer coefficients are negative. And if it was plus 25s to the 4 here, or plus 4s squared, then we could easily design substitutions to get them to cancel and so achieve helpful form in the way that we've seen several times already. But as it is, this is basically an unhelpful expression. So Diophantus had a more cunning thought. If we set both 5s squared minus 3s and this side length here to be a given multiple of s, we're going to have helpful form here that we can figure out at the end, and we reduce the problem to this subproblem of finding 2 squares that add up to 5. So this isn't completely trivial because we can't use 5 equals 1 plus 4. We need our unknowns to be distinct, and we've already used s squared and 4s squared. But we've got the tools already to find another solution to this equation, 2 squares adding to 5. We can design substitutions to make that 5 cancel by setting the squares sides to, let's say, 2 minus t and 2t minus 1. If we try that, the equation reduces to 5t squared equals 8t, so t equals 8 over 5, and we see that 5 is 2/5 squared plus 11/5 squared. And then armed with that fact, we can go back and say, well, let's set 5s squared minus 3s to be 2s over 5. That allows us to derive a value for s, and then we can check it and see that it does in fact produce a solution with distinct and positive rational numbers, as Diophantus requires us to do. So our final problem for this video is this one, which I've just slightly reworded from the original. Find a number that's the difference both between 2 rational side lengths and between the cubes on those sides. Well, just very briefly, thinking in modern terms, it's tempting to assign x and y to these side lengths and do some factorising, because x cubed minus y cubed has x minus y as a factor, and so you could divide through and you'd find x squared plus xy plus y squared equals 1, which is the graph, where when translated into a graph, that's the ellipse that you can see here, and we're effectively looking for points with rational coordinates on a particular arc of that ellipse. But of course, this is not the way that Diophantus thought about the problem. He only had his one unknown symbol to use, and he didn't really think so much in terms of factorisation. So how would he have done it? Well, as a first try, let's say that the distance between both the sides and the cubes is s, and we'll call the smaller side length, let's just say 2s, and see what happens. Then we get s plus 8s cubed is equal to the cube of s plus 2s. We can then derive s equals 19 times s cubed and read off that s needs to be 1 over root 19. Well, the problem is that this isn't a rational number, so Diophantus wouldn't allow it as a solution. So rather than just giving up on that and trying a different approach, let's analyse what it would take to tweak this 19 to produce a square number. So this 19 is the difference between the cube of the 2 here and the cube of 1 plus 2 here. So if we want to replace the 2, we formulate the following subproblem of how to do it well. Find a rational number such that its cube and the cube of one more than it differ by a square of a rational number. Well, call the unknown in the subproblem t, what we need is 1 plus 3t plus 3t squared to be a square. It's easy to convert into helpful form by cancelling the t to the 0 term. So let's say the side square is going to be 2t minus 1. That gives us 4t squared minus 4t equals 3t squared plus 3t, so t equals 7. So we can then return to our subproblem, replace this 2 with a 7, and we have that s plus 343, that's 7 cubed, s cubed, equals 512 s cubed. S squared turns out to be 1 over 169, s turns out to be 1 over 13. We could also derive this straight from the 13 that we've got over here in the subproblem, but it's safer to double check each step just to make sure that we're dealing with positive rationals all the way through. Well, that's more or less it for this video, other than to show you these bonus problems in case you want to go away and have a think about them. I hope you can see now how Diophantus broke down harder problems into 2 steps, sometimes actually even more than 2 steps. We've seen a couple of special issues which are going to be the topics of the next 2 videos in the series. First, that idea of applying a scaling factor in the first 2 problems, and we scale down by powers of s. And secondly, the question of finding squares that are a given distance apart. We had to find some squares that were 9 apart. Diophantus does some clever things with scaling, and he has a special method for finding pairs of squares that are a set distance apart. So I hope you'll continue to my discussion of those in the next videos. Do subscribe to the channel if you'd like to get notifications when I produce new stuff. Meanwhile, thank you very much for watching.